Mechanical properties of materials. Introduction. Materials are subjected to force or loads during their services. In such situations, it is necessary to know the characteristics of materials and to design the members from which it is made of, such that any resulting deformation will not be excessive, and fracture will not occur. The mechanical behavior of materials reflects the relationship between its response to deformation, for an applied load or force. The mechanical properties of materials are ascertained by performing designed laboratory experiments that replicate as nearly as possible the service conditions. Factors to be considered include the nature of the applied load and its duration, as well as the environmental conditions. It is possible for the load to be tensile, compressive, or shear, and its magnitude may be constant with time, or it may fluctuate continuously. Application time may be for only a fraction of a second, or it may extend over a period of many years. Service temperature may be considered as an important factor. The mechanical properties depend on the composition and microstructure of materials. There are different types of forces or stresses that are encountered in dealing with mechanical properties of materials. Tensile, compressive, shear and bending stresses. In general, stress is defined as the force acting on the unit area over which the force is applied. Strain is defined as the change in dimension per unit length. It may be useful to think about stress as the cause and strain as the effect. Typically, tensile and shear stresses are designated by the symbols sigma and tau, respectively, whereas tensile and shear strains are represented by the symbols epsilon and gamma, respectively. Tensile properties. One of the most common mechanical properties is tensile property. Tension test can be used to ascertain several mechanical properties of materials that are important in design. Elastic and plastic deformation. When a piece of metal is subjected to a uniaxial tensile force, deformation of the metal occurs. If the metal returns to its original dimensions when the force is removed, the metal is said to have undergone elastic deformation. The amount of elastic deformation a metal can undergo is small, since during the elastic deformation the metal atoms are displaced from their original positions but not to the extent that they take up new positions permanently. Thus, when the force on a metal that has elastically been deformed is removed, the metal atoms return to their original positions and the metal itself return back to its original shape. If the metal is deformed to such an extent that it cannot fully recover its original dimensions, it is said to have undergone plastic deformation. During plastic deformation, the metal atoms are permanently displaced from their original positions and take up new positions. The ability of some metals to be extensively plastically deformed without fracture is one of the most useful engineering properties of metals. Engineering stress and engineering strain. Stress and strain are two very important intrinsic properties of any material that have a far-reaching consequence in the application of the material in the field of engineering is concerned. Engineering stress and strain. Engineering stress and strain are very important properties of materials that have far-reaching consequences in the application of the material in the field of engineering. Engineering stress sigma equals force acting by area of cross-section equals F by 8. Unit equals Newton per meter squared. Engineering strain. When a uniaxial tensile force is applied to a rod, it causes the rod to be elongated in the direction of the force. Such a displacement is called the strain. By definition, engineering strain, caused by the action or a uniaxial tensile force on a metal sample, is the ratio of the change in length of the sample in the direction of the force divided by the original length of sample. Thus, engineering strain EPSLION equals change in length divided by original length. Unit equals meter per meter. Thus engineering strain is a dimensionless quantity. In most cases, the engineering strain is determined by using a small length, called the gauge length, within a much long sample. The unit for engineering strain epsilon in SI unit is meter per meter and the same for FPS system is inch per inch. Thus, The engineering strain is a dimensionless quantity. In industrial practice, it is common to convert engineering strain into percentage of strain. Percentage of elongation as follows. Percentage of engineering strain equals engineering strain into 100%. Shear stress and shear strain. So far, we have discussed the elastic and plastic deformation of metals and alloys under unit axial tension stresses. Another important method by which a metal can be deformed is under the action of a shear stress. Shear stress equals shear force, S divided by area over which shear force acts, A. The unit for shear stress is the same as for uniaxial tensile stress. That is Newton per meter squared. The shear strain, gamma, is defined in terms of the amount of the shear displacement divided by the distance, h over which the shear acts, or shear strain equals A, divided by h, equals tan theta. For pure elastic material, the proportionality between shear stress and shear strain can be represented as tau equals G into gamma.